Our next distinguished speaker, Frank Eisenhaber. Frank has very wide range of experience from mathematics to biophysics, molecular biology, and medicine. He had training in mathematics in Berlin, and then he moved to Moscow. We are talking about 1980s, but it's not. And he got his PhD, molecular biology, and medical degree also from Moscow. He's currently the director of biomedical informatics at Eisenhaber. He's significantly into the field of the genomics and bioinformatics, and it's a great honor and pleasure having you.
So, good afternoon, everybody. I hope you hear me well. Yes. I have no slides prepared that present the Bioinformatics Institute to you. Maybe just a few introductory words following the tradition of previous speakers. The Bioinformatics Institute was founded in 2001. I had my first visit to that institute in Singapore in 2006, and I was privately asked by certain people in charge about my opinion. At that time I was a little frustrated, and as I thought about how they can get away with obligations that will not deliver scientifically and in other directions. In 2007, I got a telephone call. At that time, I worked in Vienna, that I'm ready to take the suicidal job of giving this institute a turnaround. We struggled very hard. Essentially, the institute was reinvented as a research place. The most important thing here is, let's say, bioinformatics is a very collaborative type of science. Yeah, let's say the extrapolation depth in biology is not very big. Yeah, because theory is not very strong. Major things in life science are not known, and every progress depends very much on the interplay between theoretical and experimental work, similar to what Birgit has described in her presentation about the structure finding of Engelhardt. Yeah, so and I think the main thing in relaunching the institute was, let's say, having the confidence to reject proposals of collaboration. Yeah, so if we see that people come to us with some effort that will draw a lot of resources, but with possibly not very important outcome, we reserve the right of rejection. And this has disciplined our collaborators quite substantially. Yeah, so from then on, the thing went upward. Now BRI is known as a boutique institute in Singapore that people apply to when they want to have a non-mainstream solution of some scientific effort. Yeah, the institute has grown from something like 80, 90 people to 140 people now. We run, in addition to the natural organism library effort, that by the way was given to BRI as the Life Science Research Institute with the widest biological scope. Yeah, I think that was the major reason why we got the library and nobody else. Yeah, because other institutes would be interested maybe in some section that produces oncological drugs, or others would be interested in a section that has compounds that have immunostimulating properties or so. For us in bioinformatics, an organism is an organism. It has a genome, and our task is to predict how the genome translates into phenotypic properties. Yeah, so therefore, so we have the natural organism library. We run an genomics infectious disease program. It's part of the WHO effort of infectious surveillance worldwide. We have a program for food and chemical safety in the institute, which surprisingly has huge computational components. We have the precision medicine effort in BRI. We run the database of academic clinical trials in Singapore. And in addition to, we have a wide range of sequence structure and bioimage research efforts either run as an internal research project or in collaboration with outside institutions. How to relate this? Yeah. The first thing, since you are mostly from the engineering side, a few words, what does it mean to know the biomolecular mechanism? Yeah, so usually translating something from the discovery of the mechanism into biological, medical, or technical application takes a lot of time. Therefore, I take a piece from literature to illustrate it. Yeah, chronic myeloid leukemia had been a deadly disease when I was a school kid. Yeah, usually people died after an activation phase within a year or so, and there was no treatment. When I was a medical student, I was shown this article published in 1960, where doctors communicated an observation that many patients with chronic myeloid leukemia have chromosomal aberration that can be seen in a microscope. It's the so-called Philadelphia chromosome. Sequencing has shown that this Philadelphia chromosome is formed by a fusion of pieces of the 9th and the 22nd human chromosome. And most importantly, at the place of fusion, a new gene is formed. A new gene, which as a part has a permanently activated kinase. Yeah? And this kinase, this permanently activated kinase, is the driver behind the proliferation of white blood cells that essentially drives the patients to death. It took something like 20 years after this discovery of the Philadelphia chromosome to translate the problem into an engineering effort. Yeah? Once the mechanism is really clear, then engineers can get in and try to develop a procedure how to stop this deadly molecular mechanism. Yeah? And it was the first time that the drug was designed to fit a cavity in a new enzyme that was structurally resolved with crystallography. Yeah. And this new drug called imatinib was designed to stop this BCR-ABL fusion enzyme. And I know from the people involved in this last phase of the development that the regulatory agencies were very skeptical, and they allowed to carry out the trial only on terminally ill patients, which were known to die in a couple of weeks. To the surprise of everybody, most of these patients appeared cured after the application of the drug in the clinical trial. Yeah? So the take-home message is here. Every true, let's say, significant development in biological, in medical application, it takes about 200 discoveries to make it work. Yeah? And these discoveries involve fundamental biology, maybe chemistry, maybe engineering, maybe even mechanisms how to distribute this to the patients, maybe how to advertise this among the doctors so that they give this to their patients and so on. Yeah. The knowledge of the genome code structure-function relationship is absolutely critical for designing a cure here. Yeah, so the fact that it was discovered that the fusion protein is a permanently activated kinase, that was the basis of everything. Without that piece of knowledge, nothing would work. Yeah. It opens the perspective of treating cancer like infections. I'm quite sure that already, maybe not my children, but certainly my grandchildren will not die from cancer. Yeah, because in every type of cancer where the molecular mechanism is understood, and this will increasingly be getting the case, a mechanism or a cure can be designed to exactly stop that pathological mechanism. Yeah. Okay. One example out of our own research that tells you what kind of hidden body of knowledge there still is to be discovered. Yeah? There's a gene, SUGCT, it's a human gene. The only known thing of this gene was that in 2008 we predicted that this might do something with D acids in the human body. It was later found that patients who suffer a mutation, they have lots of glutarate in their urine. And from the enzymatic point of view, it was understood that it's catalyzing glutaminyl coenzyme A. But nothing phenomenological was understood. What is the function? What's the exact function? It was found, I make it short because we don't have so much time. It was found that we found in our institute that mice with such a knockout, they have chronic inflammation of their liver and their lungs. Otherwise, there is no phenotype. Of course, glutarate in the urine together with a little bit of other metabolites. The strange thing is if you treat the mice with a knockout, with antibiotics, they have a urine like normal mice, and the inflammation of the kidney and the liver goes away. It's also interesting to see that if you let knockout mice live much longer, essentially a group of mice lived longer than by accident. Yes, and definitely the person that needed to care for them went into holiday and didn't kill the mice as she should before going away. It was found out as a result that the mice with a knockout tend to become obese. Yeah, it's that means SUGCT is an enzyme in the reserve pathway to process glutarate and similar metabolites, which mostly come from the bacterial microflora in the gut. And if this enzyme is not functional, on short term nothing happens, but in the long term mice and people develop a metabolic syndrome as a result of the insufficient detoxification of residual metabolites from the microflora. Yeah? It tells you that many of the genes which are functionally non-characterized might have effect in special life situations of organisms or in the long term when they age, and hundreds or thousands of the functions of such genes is not understood at this point. Yeah. So we have been in the area of gene function discovery since the last 3 decades, and we wonder about the relatively small progress in many areas of the genome. Yeah? And our experience tells us that the appearance of new genomes, of new gene names, can essentially be used as a macro indicator of the novelty of life science research. Yeah, so every time new genomes appear, new gene names appear in the literature, it means that the discovery of a new biomolecular mechanism gets reported. Yeah? Whereas if the same gene names get repeated again and again, then most likely what we read is incremental research. Yeah? And we tried to map all the life science literature that was produced during the history of mankind onto the linear human genome. These are the heroes who joined me in that effort and didn't consider the task useless. I want especially to mention Lars Juhl Jensen, a friend of us at the Copenhagen University, who was very supportive in putting together the body of literature and crunching the natural language in the articles. Yeah. In principle, the growth of life science literature should be a sign of great joy. Yeah. You can see that there was essentially growth with every year until 2000, and the pace of growth of life science literature increased even thereafter. Yeah. So, for example, in 1970, per year there was in total there was 1 million entries. In 2000 we had 10 million entries, and it took only 17 years to more than double this body of literature. Yeah. So let's say you think that in principle we should know more and more, and let's say everything is fine. Yeah. So, but when we map this body of literature on the genome, then we find a horrifying outcome. Yeah. So a few methodical issues here. We put all together all the articles available in PubMed, in the patents, and Medline, and all kinds of journal websites. In total, we found something like 20 million pieces of life science literature, out of which 5 million mention gene names. Yeah? And then we counted how often a gene name is mentioned in one article, and we considered that a fraction of this article is dedicated to that specific gene. If, let's say, for example, let's say 10 times a gene was mentioned in an article, and 8 times we mentioned one gene and 2 times another gene, then we would say 80% of this article is about the gene A, and 20% is about of this article is about gene B. Yeah? That's what we call the fractional count of mentioning the gene. And 1 FPE, for all of those who have some relationship to HR, there is 1 FTE. 1 FTE is 1 full-time employment equivalent. Yeah? 1 FPE is 1 full publication equivalent. It's an idealized article that's only about 1 gene. Yeah? So, this is the finding for worldwide literature until 2017 for protein coding genes. You see that, let's say, for example, about 2,000 genes, which represent 11% of the genes ever mentioned in the literature, are mentioned at least, let's say, a fraction of a time in the literature. And this is 200% of the total life science literature. Yeah? Or let's say 5,000 genes have been mentioned in up to 10 articles. Yeah? This is a quarter of all genes, and this represents 0.5% of all the life science literature. At the other end, we have 1,610 genes which attracted more than 500 articles, yeah? And they represent 3/4 of all life science literature about genes, about protein coding genes. Yeah? Or similarly, 3,000 genes are mentioned in 100 to 500 articles. This is 18% of all genes, and this represents 15% or 16% of the whole literature. You see there is a group of 4,800 aristocrat genes, which accumulate something like 95% of all scientific literature. And about all the other genes, there is written very, very little. Yeah? Especially for a large group of genes, 6,500, there's almost no literature. Yeah? And you should add here another 4,000 genes, because there is not a single article about those 4,000 genes. Yeah? So in total, there's a group of 10,000 genes for which we have no or almost no literature, and we have about 5,000 genes which have attracted most of the articles. Yeah? It's an unsatisfactory situation, and maybe the trends are good. Yeah? People stop working on the genes that we know very well, and instead focus on the stuff that we don't know. Yeah? So I just omit some stuff. This slide here. Here we calculated how many genes cross a certain volume of literature in a certain year. Yeah? So for example, this T0 means how many genes have been mentioned in that year for the first time. Yeah? T1 means how many genes reached in this year, including the previous history, one full publication equivalent. Yeah? Or let's say this curve here, T500, how many genes crossed the threshold of 500 full publication equivalents in that year. Yeah? So you see the blue curve here is shown here, and there's a very interesting behavior. It's an erratic increase until 1975. Then there's a boom in 1975. After this boom, there's a steep increase until 2000. And there's a deep decline after 2000. Yeah? Similarly, for the threshold 500, you see there's a gradual and increasing increase until today. Yeah? So, how to explain these curves for the first appearance? Yeah? I think until 75, gene-related research was almost not present in the literature, yeah, because the idea of genes was generated in the early 60s. Yeah. There was some protein-related research before about, let's say, maybe a couple of hundred proteins, but not more. In 1975, many professors which got their position in the 68 revolution in the expansion of the universities, published their first article, and at that time a typical professor took his private gene and would start research on that private gene, yeah, and describe function and other biological aspects of that gene. Yeah, so, and until 2000, there was a major increase in gene function discovery to the extent, let's say, some institutions, they wanted, for example, to clarify all the functions of genes that were in cell division or in certain differentiation processes. Yeah, and as a result, the function research was extremely active. Yeah, until in the year 2000, functions of 600 new genes were published. Yeah, as a result, all the advance in medical treatment in pharmacy is based on the research in those years, because the new drugs are the inhibitors or activators of those proteins. Yeah. So what happened thereafter? In 2000, there was a presentation of the full human genome sequence, which was considered a watershed event and to stimulate future biomolecular mechanism research. We see actually the opposite happened. Yeah? After 2000, the research on genes that were unknown essentially got stalled. Instead, research on genes that are already quite well known flourished. Yeah? So you see the fastest growing curves are T500 and T100. Yeah? So what kind of reasons? We will talk about that later. This is a quantification of what I have described from the curves at the previous slide. You see here, in the early period, there was mainly research on unknown genes. This trend enhanced in the period from 1980 to 2000. The strongest growth is in the rows for genes which are not that well understood. And after 2000, the research on genes that have not been studied before essentially collapsed. Yeah. Yeah. What we see is there's a trend for strong superlinear growth of new function discovery until 2000. There's a steady decline of new function discovery after 2000. The accumulated deficit, by the way, from 2000 to 2018 is about 2,000 protein functions. That means the body of not very well studied proteins would be reduced from 10,000 to 8,000. Yeah? But essentially this is 2 lost decades. During this time, not much has been added here. And the presently fastest growing group of proteins is the group for which already a huge body of literature is available. For example, you have all heard CD40, P53, insulin, and so on. These types of targets you see again and again in the biological and medical literature. Yeah? But rarely studied genes like SUGCD or some of the 4,000 that have not been named at all, you will look for with great difficulties. Yeah? So there's another dimension of the problem that the human genome is not only protein coding genes, lots of RNAs have also important biological function. And a similar type of research shows that there is 120 aristocrat RNAs which accumulate, which attracted, let's say, essentially all the literature about human RNAs. Yeah? And there's another 2,000 RNAs which are somehow mentioned, but there's no big body of literature about them. And tens of thousands of RNAs which are also there, nobody cares about. Yeah, so I will omit that. Yeah, if we extrapolate, if the pace of protein coding function discovery continues like in the last 2 decades, it will take another 100 years until the function of the last protein is discovered. Yeah. Yeah. And until that happens, fast and cheaper sequencing means only the accumulation of more non-understood sequence. Yeah. Just by having more of the sequence, we don't get any wiser. Yeah. We have made a similar study on E. coli. Yeah. We found that in E. coli there is a group of something like 100 genes which accumulates half of the literature. Many genes in E. coli have very, very little literature, and there's 300 E. coli genes which are functionally unstudied even today. Yeah. So similarly, the function discovery in E. coli is going down since 2000. Yeah, and a similar situation in yeast. There's about 100 yeast genes which have the greatest part of the literature, and the yeast gene function discovery is also going down since 2000. Yeah. You can ask, what is the reason? Let's say it's very, how to say, heretical to talk about that matter. I think there is several issues. The first, I would think, is function discovery is a 5 to 10 year project with total cost in the order of $10 million. Yeah? Most people don't have the luxury to operate in similar dimensions, yeah? Which was very normal in a period when researchers had budget funding from the institutions. Yeah? The second point is I have seen, let's say, how grants are distributed in various countries. I was a reviewer or even a grant commission head in many places in the European Union, in the United States, in Israel, in Singapore, and other places. Yeah, I noticed that in the commission, grants which try really new things have essentially no chance. Yeah, so assigning resources to researchers by commissions instead of bright individuals will also put down let's say interesting research. Yeah, and the final thing is when I was a postdoc, together with my colleagues, we laughed about the 5-year professorships that many institutions offer. Yeah, and we thought, who will be the idiots that pick up such offers? Yeah, not understanding that's our generation to run into such short-term contracts. Yeah, and with the pressure to deliver something substantial in 2-3 years minimum, yeah, if not earlier, you cannot run very risky projects, and you have to focus on incremental efforts that will deliver articles in a year's effort. Yeah, so I think the complex of all these things will lead us to the decline is that drastic. Yeah, and to tell you the truth, it's the more worrying because the function discovery articles usually didn't come from the University of Cairo, Dhaka, or let's say Cape Town. Yeah, but the function discovery articles typically come from Harvard, Stanford, Yale, EMBL, the top British or French universities, and so on. That means the decline in this literature is because of the decline of the top institutions, yeah, which avoid the really difficult questions, which is a new trend, which was not the case until 2000. Yeah. So, despite tremendous societal, biomedical, and biotechnologies needs will not be satisfied in many years to come because there's no molecular mechanism inside. You cannot treat a disease without understanding the molecular mechanism. Yeah, of course you can be lucky, like in the lottery. Yeah, but in most cases it will not work. Yeah, there's a dramatic improvement in all cases where the molecular mechanisms are known. Yeah, and there is a great market for charlatans of all kinds who will promise to provide healthcare advice based on the genome information. Yeah, I can tell as a scientist that you can study the genomes, you can give lifestyle advice, but to link the two scientifically is impossible except for very minor cases. Yeah, so that's it. Thank you very much for your attention.